Okay, so welcome back to my channel. So in today's videos, what we're going to be looking at is the multivariate OLS model. So previously we've learned the single variate case. So let's say we're going to still use the same example. We have our y, dependent variable y, which is going to equal to beta 1 plus x1 beta 1, where y just represents the income, and also our xi is just going to represent the year of education, okay, of education. But in practice, we know that people's income level are more likely to depend on more than just one factor. So we might also think that the income level probably going to be depends on, for example, x2 beta 2, and this x2 going to represent, let's say, age. Yeah, because so commonly speaking, like the more time you spend on that job and the more experience you're going to obtain, and so that your incomes will also increases accordingly. So, and also we probably have some other factors, and all the way to xk, beta k, and plus our arrow term mu I. And here we're also going to assume that for each individual xi and xj, the covariance of xi and xj going to be equal to 0, which means given any two independent variable xi and xj, so they must not be dependent with each other, okay? And so as the arrow term mu, the mu I should also, like the covariance of mu I and any xi should also be equal to 0. So the arrow term is also totally independent with any given xi or xi. So with this model being set, let's say we collected several data. Let's say we have n data, our population, our sample. We have n sample. Y1 is going to be equal to beta 0 plus, let's say, x1. 1 represents the factor 1. No, actually, the 1 represents the index of the data set. Okay, so x1, 1. The second one represents the factor. So this is the factor 1 and beta 1, and plus x2, 1, x1, 2, I'm sorry, beta 2, and plus all the way to x1k, beta k, times mu 1. Okay, this is for our sample 1. And for sample 2, we have y2 equal to beta 0 plus x2, 1, beta 1 plus x 2 beta 2 plus all the way to x2k beta k plus our mu 2, and all the way goes down to yn, which is going to be equal to beta 0 plus xn1 beta 1 plus xn2 beta 2 plus all the way to xnk beta k plus mu n. So if you have, so we have equation sets for each individual sample, and if you're familiar with linear algebra, so this form we can also rewrite this as y, the vector y, going to be equal to the matrix x times the vector beta plus our vector mu. So for our vector y, we have y1, y2. It's a column vector. So let's start from y1 all the way to yn. And for our matrix x, we're going to define it as, for the first column for the x should be 1, 1, 1, all the way to 1. Because we have intercept, it's a constant term. And the second column is just going to be x1, 1, x2, 1, and all the way to xn1. and also the x1 all the way to x1k. And finally, we have our x and k. And this is our X matrix. And we're going to dot this X matrix with our beta column, which is beta 1, beta 0 actually, and beta 1 all the way to beta k. And finally, we're going to plus the mu column. This is our beta column, beta vector. And finally, we have our vector mu, which is our mu1, mu2, all the way to mu n. Okay, cool. So next, what we're going to do, remember we defined the loss function of our OLS model as S is equal to the sum of our mu I square. And also, if you're familiar with the vectors calculation, and you might recall that the sum of mu I is just equal to mu1 square plus mu2 square all the way to mu n square. So this is also equal to the mu transpose times mu, the vector mu transpose times the vector mu. Alright, so now we have already defined the loss function of our OLS model. So we're just going to use the exact same method, which is to take the partial derivative of each individual estimator. In our case, we have beta 0 to beta k, and which is going to be the partial derivative of our x takes the partial derivative of the beta vector. And we set the partial derivative equal to 0 and solve the function, the equation set, and we're just going to have the expression for our estimator. So now let's try to do that. So we're first going to substitute the vector mu. So this is actually going to be equal to, because we know that the vector mu is going to be equal to vector y minus matrix x times vector beta. So now we're going to have the vector y minus x times beta transpose times vector y minus x times beta. And that's the whole things we're going to take derivative with respect to vector beta. Okay. So now let's try to expand the parentheses of the numerator first. So we know that the numerator is just going to become okay, let me go to this page instead. So okay, for the numerator we're going to have y transpose times y minus y transpose times x matrix x times beta vector beta, and also minus, so the transpose of x times beta is just going to be beta transpose times x transpose. Okay, this is just the property of the transpose operator. So then we apply this property, then we have minus beta transpose x transpose times y, vector y. And finally, we plus the beta transpose x transpose times x matrix x and vector beta. And this is for our numerator. So we take partial derivative with respect to our vector beta. Okay, cool. So then we're just going to look at each term in this numerator. So for the first term, we know that the y transpose times y has nothing to do with beta. So the first term is just going to be equal to 0. And for the second term, and also here I'd like to introduce some differentiation rule for matrix. So let's say if we, let's write it here, let's PS. If we have a, let's say A times beta differentiated by beta, let's say it's a vector beta, okay, that is going to be the transpose of A. So this is actually something you should learn in the linear algebra. So today is not going to really get into detail about that, but let's just try to apply this to the second term. So the second term, we view this first things as our A, then we have the result is just going to be equal to minus x transpose times y vector y, okay. And also for the second term we have, and this is another different property, so let's say we have beta transpose times A, and take the derivative with respect to the beta transpose. That is just going to be A. Okay, let's now apply this property to the third term actually. Then what we're going to have is our beta t times y, vector y. And finally, what we have is our third term. And here's also another property. Let's say if we take derivative of beta t times A times beta, and take the derivative with respect to beta, then what we're gonna be left is A plus A transpose times beta. Okay, so we also applied this property to the fourth term, and we're gonna have plus. So the A is actually equal to the x transpose times dot x. So here we're going to be left is x transpose dot x, and plus the transpose of x transpose and x is exactly the same. So it's another, again, an x transpose times dot x, and times the beta. Okay, so this is going to be equal to 2 x transpose times y plus 2. So this, okay, so I forgot a minus sign in front of it, and plus 2, and this is going to be x transpose times x times beta. And this is our partial derivative. Remember, this is our s with derivative of beta. And we set this first order derivative equal to 0, and we're trying to solve for our beta. So the vector beta is actually equal to, which means our 2 times x transpose times x times the beta, vector beta is going to be equal to 2 x transpose times our vector y. Okay, so here we cannot just say we're going to divide it both sides by 2 times the x transpose times x, because x transpose, this is actually a matrix, okay. We cannot use the same calculation rule as we used in the scalar case. So instead, what we're going to do is to times the inverse of x transpose for both sides. Now what we're going to be left is beta, the vector beta is just going to be equal to the x transpose times x, the inverse times x transpose times our y. Alright, so this is our expression for estimator beta. Okay, cool. I will see you in the next video.